All right, hello and welcome. I'm Major Cunningham from the Astro Department, and I just wanted to put together a quick video just doing some practice of these what we call box problems. So I've got this exercise which I'd be happy to provide, and all your instructors should be able to provide this to you just as an exercise to kind of get better at this before the next GR. Okay, so I'm going to start off with number one. I'm just going to work my way down through this first page here. Hopefully this gives you a good idea of what we're up to. Okay, so the first problem here says that my semi-major axis is 8,500 kilometers, my eccentricity is 0.1, my inclination is 45 degrees, RAN is 0, argument of perigee is 180, and true anomaly is 0 degrees. And then you have all these boxes. And so it's like, well, we just want you to tell us about the orbit and, what is true about this orbit, and not everything will apply. So here's how I typically do this. I always start off here by drawing a circle. Ooh, that was a good circle. And I draw the middle of the circle. And then I draw an arrow out to the side. Turns out this is the nodal vector, or the line of nodes. Points from the middle of the Earth, starts at the middle of the Earth, and points out towards this point, which is the ascending node. And remember, that's where a spacecraft, if our orbital motion's going like this is where the spacecraft crosses from being over the southern hemisphere to being over the northern hemisphere up here. Now, what I want you to remember first of all is this is what I would call the orbit view. This is not the side of the Earth, no. This is, if I were to look perpendicularly right down or sideways, edge on to how the orbit is. And that's important because this is, if this were just the Earth, a side view of the Earth, then these would be the North and South Pole. That's not the case. This is just the orbit itself, kind of irrespective of the Earth. Okay, so the first thing I can say is that being told my semi-major axis is 8,500 kilometers, that's not that helpful. Not for these box problems. It is for lots of other problems, not for these box problems. Okay, eccentricity of 0.1. First of all, do we know if it's circular or not? Of course, first thing we remember is that eccentricity of 0 would be a perfectly circular orbit. It's not, though. It's bigger than 0. So I'm going to go ahead and cross out circular. It's not circular. All right, that's about all that eccentricity can tell us. Inclination. So inclination will be able to tell us several things here. At the very least, these four. First of all, for an equatorial orbit, inclination would have to be 0 or 180. But we see that it's 45. It's not 0 or 180. Prograde would be an inclination between 0 and 90. So is that the case that we find ourselves in? Yeah, it looks like it. 45 degrees is definitely between 0 and 90, so I'm going to go ahead and kind of fill in that box. Now, if an orbit is prograde, it can't also at the same time be retrograde, because retrograde would be an inclination of 90. Oops. Between 90, I should say, and 180. Now, it can't be exactly 90. We're going to talk about that in a second. But anyway, inclination of 45 is not between 90 and 180. So let's cross this off. For a polar orbit, inclination would have to be exactly 90. Is it exactly 90? No, it's not. So we know it's not in a polar orbit. So all we know so far is that we have a prograde orbit that's not circular. It's elliptical. Okay, now for the rest of these, we've got to go to our picture. Let's go to the video. Let's go to the picture. Okay, I drew my circle, and I drew my nodes, my line of nodes out to the ascending node. This is how you're going to start every picture. Right? This is how you're going to start every single picture for box problems if you want to do things my way. Okay, so the next thing you're going to do is ask yourself, okay, what is argument of perigee? Okay, argument of perigee is 180 in this case. So I'm going to trace out 180 degrees worth of argument of perigee. How do I know that's 180? Oh, it's just, it's half a circle. I didn't draw it perfectly, but it's half a circle. Okay, so maybe I should just make some steps here. Draw a circle. 2. draw n vector out to ascending node. Okay. Now trace out however much your argument of perigee is. All right, so that catches us up. Step 4, you're going to draw the eccentricity vector, and remember that points to perigee. Now you guys will remember that perigee is the closest point of an orbit to the Earth. We know that this does in fact have a perigee because inclination is the eccentricity is 0.1. Okay, so let's draw our E vector. You draw it basically touching the argument of perigee. And you can label that E vector. Okay, this is perigee, so we're going to label perigee. And again, this is just for this orbit, but okay, then starting off at perigee, measuring around the direction of spacecraft motion to get to the spacecraft, that's what true anomaly is. So 5. Trace out true anomaly to find spacecraft location. So this first problem presents us with an interesting issue. Our true anomaly is 0, so that means I don't trace out anything from perigee. My spacecraft is right here. Okay, so let's go back to our boxes and see what this can tell us. Okay, first things first. Is the spacecraft at perigee? Yes, it is. And the reason I zeroed in on this random one right here is because we literally just found the spacecraft is at perigee. Now, the good thing about it being at perigee is it can't also be at apogee, which would be the other side here, so we can cross that off. Each one of these usually means that another one can't at the same time be true, which is kind of the convenient thing here. Okay, so how about ascending nodes versus descending nodes? We'll just kind of work our way up. We establish the ascending node over here on the right always, because that's just how we draw the picture. It's how we start the picture off, is by drawing this line of nodes out to the ascending node. Well, our satellite's on the opposite side, literally 180 degrees away from the ascending node. That's going to tell us that we're at the descending node. And if you want, you can label that, right? DN. If it's at the descending node, it cannot also be at the same time at the ascending node. That's helpful. Okay, now let's think about k-hat. K-hat, I'll put little hats on these. Ta-da. K-hat is an axis in our IJK coordinate frame, remember, that points up through the North Pole and down through the South Pole. If our orbit is not perfectly polar, like 90 degrees, it can never touch the k-axis. It just never will. It'll never fly up over it or through it. So that means if it's not going to go through k-axis, it is not possible to be at the North Pole or the South Pole. Okay, so we're almost there. We've ruled out almost everything so far. Or rather, we've addressed all of our concerns so far, I should say. Okay, so as far as if the spacecraft is on the I-axis only or the J-axis only, I draw a top view. Not all of these problems are going to require a top view. But I'm going to draw it out here because this one does require one. So I literally draw like the ice caps, right? We're looking down through the North Pole. Like if my pencil were K-hat, that's basically what we're drawing right now. Looking down at the Earth through the North Pole. So K-hat is coming up at the, up out at you towards the camera. When you draw the top view, draw out your I-hat to the right here. And that gives you your starting point for your top view. So the question is RAN at this point. So RAN is measured from I-hat around, remember now we're looking at the top, looking down at the Earth, so along the equatorial plane, which would be kind of parallel with my Earth here, right? It would be cutting through my Earth. It would look like it's flat, cutting through the Earth like a napkin or a piece of paper like that. So you're going to draw your I-hat. And that gives you a place from which to measure out RAN. Now, kind of just like our true anomaly was 0, so we didn't have much to do, our RAN is also 0 in this problem, so we don't have that much to do. That means that our spacecraft is right there. What this means, what I'm trying to get at is it's at the ascending node. And it's literally on I-axis, right? So J, just for example, J hat is 90 degrees away. However, comma, it is not the case right now. The satellite is over on J hat. It's currently at the ascending node. Let me put it this way. If RAN were 100 degrees, we would start here at I hat, measure around, and then up here somewhere would be our ascending node, or rather over here. That would mean it's not on I or J. But the problem is literally constructed so you have to confront this issue. We know that it's at I hat because RAN is 0. It's literally not any farther away from I hat than 0 degrees. So what we know is we can fill in the I hat box, and we can cross out the J hat box, because if it's on I hat, it cannot also be on J hat or K hat. All right, that does it for this first problem.